Hi guys, so we're going to move on to lesson 6.2. Let me present my screen so we can start. Okay, so in lesson 6.2, we're going to be talking about different segments and points in regards to our triangles. So we're going to start with 3 vocabulary terms. We're going to start with concurrent, point of concurrency, and circumcenter. So when 3 or more lines, rays, or segments intersect in the same point, they are called concurrent lines, rays, or segments. The point of intersection of the lines, rays, or segments is called the point of concurrency. All right, in a triangle, the 3 perpendicular bisectors, which we discussed perpendicular bisectors in the last lesson, are concurrent. Okay, so that means that all 3 perpendicular bisectors are going to intersect at a point of concurrency. The point of concurrency is called the circumcenter of the triangle. All right, so the circumcenter theorem, it says the circumcenter of a triangle is equidistant from the 3 vertices of the triangle. If PD, PE, and PF are perpendicular bisectors, so let's think about that for a second. If PD is a perpendicular bisector, that means that, ignore that. That means that we have a right angle here, and DB is congruent to DA. And if PF is a perpendicular bisector, we have a right angle. Come on, right angle. And that means that AF is congruent to FC. And if PE is a perpendicular bisector, that means we have a right angle. And BE is congruent to EC. All right. All right. So those are your perpendicular bisectors. It then says that PA is congruent to PB, which is congruent to PC, because this theorem tells us that our circumcenter, which is our circumcenter, which is point P, that's your point of concurrency where the 3 perpendicular bisectors intersect. All right, the circumcenter of the triangle is equidistant from the 3 vertices. So this theorem tells us that PB is congruent to PA, which is congruent to PC. All right. And just again to clarify, point P is the point of concurrency. Remember again, the point of concurrency is where, I ran out of room. CY. The point of concurrency, that's where the 3 perpendicular bisectors intersect, and they have a special name. It's called the circumcenter. Sorry. All right, so that is the first theorem of this lesson. Let's move on down. All right, so here it says 3 snack carts sell frozen yogurts from points A, B, and C outside of the city. Okay, so we have frozen yogurt being sold here and here and here. Okay, each of the 3 carts is the same distance from the frozen yogurt distributor. Okay, so the frozen yogurt distributor is located somewhere where A, B, and C are all equidistant from it. All right. Find the location of the distributor. So we're going to be sketching here. We're not going to be doing exact constructions. However, I want you to focus on the terminology of the lesson. So above, we learned that the circumcenter, which is the intersection of the 3 perpendicular bisectors, is equidistant from the 3 vertices of a triangle. All right, so that's what we need to do. We need to find the circumcenter. We need to find the intersection of the 3 perpendicular bisectors. So we'll write that down. We need to find the circumcenter, which again is the intersection of the 3 perpendicular bisectors. All right, because this circumcenter is equidistant from the three vertices. So if you kind of eyeball segment AB, find the midpoint. Okay, it looks like the midpoint's about right there. And then I'm going to find the to indicate the midpoint, let's put our little tick marks. Then I'm going to find the midpoint of AC. Again, we're just approximating here. So I'll put my tick marks. And BC, it's about like right here. All right, so those are my midpoints. Now my perpendicular bisector has to go perpendicular through this midpoint. So I'm going to draw a segment that appears to be perpendicular. Then from here, a segment that looks like it's perpendicular, something like that. And then here, my sketch is not the best, but okay. So about right here is where the three perpendicular bisectors intersect. So that is where your distributor should be, okay? So the location of the distributor is the circumcenter. Because above in the theorem, we learned the circumcenter is equidistant from point B. So if I was to connect B to the circumcenter, A to the circumcenter, and C to the circumcenter, those three segments, 1, 2, 3, 4, are all congruent to each other because they're equidistant to the circumcenter. Right? Okay, let's keep on moving along. All right, next it says the circumcenter P is equidistant from the three vertices. So P is the center of a circle that passes through the three vertices. So, okay, so we have P, that's your circumcenter. And then if we were to draw a circle around the triangle so that the three vertices all sit on the triangle, right? So there is your circle. It says that P is the center of that circle. Here's another diagram. So they're showing you three different triangles. They're showing you an acute triangle where P, the circumcenter, is the center of the circle. Then they're showing you a right triangle where you have your intersection of the three perpendicular bisectors. There's your circumcenter, and it is still the center of the circle. And then we have an obtuse triangle, all right, where P is the center of the circle. But notice where P is in relation to the triangles, because that's what this is explaining. Okay, for an acute triangle, P is going to be inside of your triangle. For a right triangle, P is going to be on the triangle. And for your obtuse triangle, P is going to be outside of the triangle. All right. So as shown below, the location of P depends on the type of triangle. The circle with center P is said to be circumscribed about the triangle. All right, there's a new term for you. We're going to skip the construction. We're not doing constructions today. All right, so finding the circumcenter of a triangle. Find the coordinates of the circumcenter of triangle ABC with vertices A, B, and C given. Okay, so the first thing we're going to do is plot the triangle to see what kind of triangle we're looking at. Let me make this a little bigger so it's easier for me to plot the points. Okay, so we have point A at 0, 3. Oh, 0, 3. Here's point A. Point B is at 0, -1. Oh, wrong spot. Sorry. To go down. That's point B. And then point C is at 6, -1. All right, so we'll draw the triangle. So what kind of triangle do we have here? Does it look like it's a right triangle, obtuse triangle, acute triangle? Is this a right triangle? And how do I know it's a right triangle? Well, we have a vertical segment and a vertical segment and horizontal segment. So we know that they're perpendicular to each other. You have a right angle there. So triangle ABC is a right triangle. So think about what we learned above, okay? If it's a right triangle, then we know that the coordinate of P, your circumcenter, is going to be on the triangle. So the coordinate of the circumcenter should be on triangle ABC. All right, so we're going to find the midpoint of each side, right? Because to find the circumcenter, we need to find the location of where the perpendicular bisectors intersect. Okay, and we did this a little bit in the last lesson as well. To draw the perpendicular bisector, you first have to find the midpoint of each side and then draw the line that's perpendicular through that point. Okay, so we're going to first find the midpoint of each side. All right, so to find the midpoint of AB, luckily, we don't really have to use the midpoint formula because it is a vertical segment that is 1, 2, 3, 4 units long. So the midpoint is going to be 1, 2. The midpoint's going to be right. Oh, let me use a different color. The midpoint's going to be right here. Okay, so the midpoint of AB is located at 0, 1. Now the midpoint of BC, same thing. We don't have to use the midpoint formula. We can just count. BC is 1, 2, 3, 4, 5, 6 units long. So the midpoint is 1, 2, 3. It's right here. So the midpoint of BC is located at 3, negative 1. And then finally, the midpoint of AC. Now for this one, we're going to want to use the midpoint formula. So coordinates of A, and I can list them here even though they're written right here as well, and the coordinates of C, 6, negative 1. So to find the midpoint, you take the average of the x's, 0 plus 6 divided by 2, and the average of the y's, 3 plus negative 1 divided by 2. So your midpoint is located 6 divided by 2 is 3, and 3 plus negative 1 is 2. 2 divided by 2 is 1. So the midpoint is at 3, 1, which you probably could eyeball, but there we go. Okay, so that's the first step, is identifying all the midpoints. All right, now let me clear this so that I have more room to write. All right, now remember the goal is to find the intersection of your perpendicular bisectors. So if you are able to draw a line without having to calculate the slope and do all that, then go ahead and do that. So if this is a vertical line, the line that's perpendicular is going to be a horizontal line. So I want to draw a horizontal line through the midpoint. That is the perpendicular bisector of side AB. For side BC, since it's a horizontal line, the perpendicular line is going to be a vertical line that goes through the midpoint. So that's the perpendicular bisector of BC. All right. Now, I could, and I will, find the line that's perpendicular to AC, but I can already see that the two perpendicular bisectors intersect right here. And we also said that the circumcenter should be on triangle AC, so that is going to be my circumcenter. But let's just go ahead for practice. The slope of AC, right, if I go from A to C or C to A, it doesn't really matter. You're going down 1, 2, 3, 4 units. Did I count right? 1, 2, 3, 4 units. Yep. And then over 1, 2, 3, 4, 5, 6 units. So down 4, over 6. Simplify that to a negative 2/3. The slope of AC is negative 2/3. So the slope of perpendicular to AC is going to be a positive 3 over 2. So that means from the midpoint of AC, I can go up 3, 1, 2, 3 over 2, 1, 2, and plot a point. There we go. Up 3, 1, 2, 3 over 2, and plot a point. Okay. Or it could go down 3, 1, 2, 3 over 2, plot a point, down 3 over 2, plot a point. So if I draw a line through all of those, That is the perpendicular bisector of side AC. So I can see that all three perpendicular bisectors intersect right here, which is your circumcenter. So the coordinates of your circumcenter are, what is that, 3, 1. And there you go. All right. So that was a multi-step problem, but not too bad. Let's keep moving along. All right, using in-center of a triangle. So just as a triangle has 3 perpendicular bisectors, it also has 3 angle bisectors. The 3 angle bisectors of a triangle are also concurrent. This point of concurrency is called the in-center of the triangle. Okay, so make sure you know the difference between the terminology and the vocabulary words. For any triangle, the in-center always lies inside the triangle. All right, so you can see that the red segments AP, PB, and PC are all angle bisectors. Is also explained here. Okay, so if AP is an angle bisector, that means this angle is congruent to that. If PB is a angle bisector, that angle is congruent to that. And then PC, 3 arcs, those angles are congruent to each other. All right. It says the in-center of a triangle is equidistant from the sides of the triangle. So if you go from the intersection of your angle bisectors, which is point P, that's your in-center. The in-center is equidistant to the sides. And we draw the distance with a perpendicular segment, but that's just saying that PD is going to be congruent to PE, which is congruent to PF. Okay, so that's what this theorem tells us. So let's keep on moving along. Example 3, using the in-center of a triangle. It says in the figure shown, ND, okay, so I gotta get my pen. ND, this length right here, is 5x minus 1, and NE is 2x plus 11. Find NF, okay? Well, I see that let me name them a different way. I see that NB, NA, and NC are angle bisectors. All right. So that means that point N is the point of concurrency. And remember, the point of concurrency for angle bisectors is called the in-center. Right? And we just learned above the in-center is equidistant to the sides of the triangle. So what does that mean? That means that ND is congruent to NE, which is congruent to NF. All right, so that tells us that ND is equal to NE, which is equal to NF. All right, NF. All right, so we're going to use that information to find the length of NF. Okay, so if this piece here is 5x minus 1, and then NE is 2x plus 11, I can set those equal to each other. So ND is equal to NE. Therefore, 5x minus 1 is equal to 2x plus 11. I can solve for x, so subtract 2 from both sides. 3x minus 1 is equal to 11. Add 1 to both sides. 3x is equal to 12. Divide by 3, x is equal to 4. So I know x is equal to 4, which means that ND is 5x minus 1. 5x minus 1. That's 5 times 4 minus 1. That's 20 minus 1. That's 19. All right. ND is 19. NE should also be 19 because they're congruent. So 2 times x plus 11. 2 times 4 plus 11. 8 plus 11. It's 19. All right. And then NF should also be, I think I pulled this down a little bit. NF should also be equal to 19 because they're all congruent to each other. Okay. So I just found, I'm going to erase all this. I just found that NF is equal to 19. All right. And X was equal to, what was it, 4? I think we said. I forget already. I won't put that over here just in case we need it. All right. Then it says here, can NG, so this segment here, can NG be equal to 18? Explain your reasoning. So think about that for a second. This is 18. They're saying, can it be 18? Excuse me. And NF we just found to be 19. Okay, does that make sense? Can this be 19 and this one be 18? Explain your reasoning. What do you guys think? It's a few different things we could say as far as the reasoning goes. I'm going to focus on this right triangle right here. Okay, so NFG is a right triangle. That's 19. Can this be 18? Well, isn't NG the hypotenuse of the right triangle? Doesn't the hypotenuse of the right triangle always have to be the longest side of the triangle? So it can't be 18. Okay, that's one thing you could say. All right, you could say that if you look at this right triangle, the hypotenuse NG has to be the longest side. So it can't be smaller than NF. NF can't be 19 and NG 18. That doesn't make sense. Also, whenever you're finding the distance between a point and a line, we use a perpendicular line segment, and it's the shortest distance that we're finding. So NF is the shortest distance from point N to line AC. All right, so it's another way you could justify why NG cannot be 18. Okay, so you can write down one of those two reasons. And guys, I think that is it. We're not doing the last examples. So that is the end of lesson 6.2. Let me just erase this. Oop. Come back here. That's the last part of this lesson. So I'll see you back here for the next one. Bye.